So thank you everybody for joining us for Spark-powered Scylla. My name is Eyal Gutkind. I'm a solution architect at ScyllaDB, and that's me basically. Let's start with it. So a little bit about Scylla. Scylla is a next generation NoSQL database. It was incepted and created by the people who created the KVM hypervisor. So we are very, very familiar with how underlying asset works. And this is how we take advantage of those resources in our database to create a very performant, low tail latencies into our database. Scylla is a drop replacement for Cassandra. It means that every API, whether it's the management or the actual protocol that connects to your application, is identical. So you can take out your Cassandra cluster and put in a Scylla cluster instead of it. We offer two versions of the product. One is the open source and the other one is the enterprise. Please visit our website, ScyllaDB.com, to learn more about the differences between those two offerings. We have headquarters here in Palo Alto, as well as in Herzliya, Israel. And if you're interested, check our hiring tab. So let's just dive into that. So why Spark with Scylla? So as you already know, Scylla is a scalable, highly available database. Scylla scales linearly while providing a fault-tolerant architecture for your real-time big data application. Whether you use it on-premise or cloud-based infrastructure, Scylla is a solution that offers performance, scalability, and durability to your data. Granted, data is stored in a columnar table-like format, which is inefficient for transactional workloads. Put it in other words, we sometimes see Scylla more suited for OLTP workloads, minus the normalization data of data and the ER modeling. We denormalize and we have no relational capabilities. That's what Scylla is typically used for. So, okay, what about analytics workload on top of that data? Well, in most cases, users would yank out that information from the transactional system and move it to the analytic platform. However, today, users can deploy analytics workloads on the information stored in the transactional system. During this presentation, we will be showing also a demo how to do that. So we will show exactly how we transition between the insertion of the data and retrieval of the data, and how we deploy that performance on top of our clusters. With that, I will do the following. I will switch out of the presentation mode. And I do have a Spark. I'm just going to show the demo that we're going to show work during this presentation. We have a Spark master with basically 8 slaves, 8 different nodes. And we have also a 3-node cluster of Scylla that backs it up from our perspective. I will go ahead and fire up a job. There's a table that we created before inside our system. It's basically an airline traffic information that travels between, that defines how much delays we are seeing on our side. So I'll go ahead and basically drop the table from our perspective. Oh, sorry. And once it's done, we're going to go ahead and I'll just show you that we insert the information into the cluster itself. Okay, so this is what we do. Sorry. We'll submit the job. Perfect. While that runs, we will go back to our presentation. So let's talk a little bit about the mechanical parts of how Scylla is storing information. So Scylla, as Cassandra, uses a token-based sharding of data. Data is distributed among the different nodes by ranges, where every node is quote-unquote responsible for part of the data. The data is tokenized into a specific range and stored in that range until data resharding is needed. For example, if we add a node or remove a node from that cluster. The above graphic is a simplistic view of the way the data is being stored into Scylla. We disregarded the vnodes notion in this specific case, just for the simplicity of visualization. However, vnodes add an additional layer of resiliency and distribution of the data across the nodes, and we use that performance capabilities as well as resiliency for a more performant retrieval and insertion of information to the database. So in such a way that if the case of a range is failing, you don't lose 1/3 of the data immediately, but the burden of losing part of the data is shared between the different vnodes. You can read more about the vnodes implementation as well about the architecture itself of Scylla in the link that you see here below on our slide deck. So let's talk a little bit more how we actually go into the translation of tokens into a specific entry that is placed into a Scylla cluster for nodes. So let's look at the partition key. And it is translated into a token using a non-cryptic hashing function. In our case, we use a mem3 hashing function. And once the partition key is hashed, the driver, the client driver, places that portion of data into the cluster and knows exactly which node should be contacted in order to insert the information. The hash key is then written or read to the designated node in that specific ring. For example, as we see here, the hashing functions take that partition key and push it into node X. The hashing function guarantees an evenly distributed data given different partition keys are used for each record. So every time you insert a data with a different partition key, it's going to be inserted statistically on a different node. So you'll have a very evenly distributed data across the cluster. Why is it relevant for our case in use case? Spark jobs rely on the data locality, meaning Spark will try to place tasks into a node that actually holds that information. So Spark also expect that some level of data continuation or streamline in that specific partition is existing, and when you fetch or write data, you actually go in a continuous manner. However, with Scylla and Cassandra for that purpose, that continuation and locality of data is a little bit challenging as the distribution of the data is extremely evenly distributed across all the nodes. So a single partition, which should be basically gathered into a single chunk of data for Spark, are now distributed across multiple nodes in the cluster. So that's a challenging part for the Spark perspective. Let's jump a little bit and explain about how Spark do this histories. So a little bit about Spark architecture to help us understand the connection between Scylla and Spark. So Spark is a distributed execution system. At a high level, every Spark application consists of a driver program with a cluster manager that runs the user function, the actual jar that we provided. That function goes to a different parallel operations on the node. So we have executors, which each one of them is a node in our cluster. Each executor is assigned with multiple tasks, and those are being executed in parallel. The information is stored in what we call resilient distributed dataset, RDDs, which is a collection of elements partitioned across the nodes of the cluster that are operate on them in parallel. Once the execution of the data is completed, all the results are handed back to the driver program for aggregation and reporting back to the user. Spark is a lazy program. Data transforms are not executed until a summary or a computation job is called. So if there is, for example, a transformation you're doing on the data itself, it's not going to happen until you actually retrieve that information from that specific RDD. Let's look now how data is stored in the executors themselves and how that impacts the connection between Scylla and Spark. Oops, sorry. So each node memory stores multiple RDDs. Think about it that you have multiple tasks that runs in every one of those nodes, and those RDDs are actually partitioned based on the evenly partitioned across the different nodes. And partitions in RDD contains a block of data. The number of partitions is determined by the number of cores, threads that you have in the system. Users can define a per task number of partitions to use, or let the Spark job distribute itself evenly across all the nodes. One thing that we have to concentrate about is the effect of locality of the data, as we mentioned before. And Spark in its design have the data processed locally. It means that the data is fetched into the RDD and is located as close as possible to the RDD node. In our case, Scylla Cassandra, it's not that easy done. Let's jump a little bit more into the RDD look. So how that fits, how Scylla, or the partition of Scylla, fits into the notion of the RDD itself. We have to remember that the Scylla partition is not an RDD partition. A Spark RDD partition includes multiple Scylla partitions. The best case is if the data is continuous when we fetch. However, as we described in a minute ago, the beginning data is scrambled due to the Scylla cluster murmur3 hashing function. And that means that every partition will be in a different node. Partitions in Scylla are scattered in the cluster. It means that you have one coordinator who goes and read the information from different nodes and give them back to the RDD. And that is creating some challenges in putting data into the cluster and retrieving itself as well. So how does it happen at the end of the day? Well, there is a Spark Cassandra connector that provides exactly that, a context, a Spark context to Scylla Cassandra for a Spark job. It was developed by the DataStax team, and it's an open source connector that you can download or use directly into your application. The connector will create a connection that provides an IP address of the Scylla nodes to the Spark driver cluster. The connector itself is built upon the Cassandra Java driver and uses all the parameters that the Java driver has underneath it. Currently, the driver itself is packaged into the connector. So if you actually want to do any changes to the Java driver settings, you'll have to download the connector itself, recompile it again with different settings that you might want to use. One thing that a couple of things that we have to mention here. The first thing is that every time we write with the Spark Cassandra connector, we batch. We'll talk about batches in a minute, but that has huge impact about the performance and the capabilities of writing information in and out, writing into Scylla. When reading, it also has its own ways to fetch information from the RDDs themselves in terms of the sizes of the blocks. So we'll talk about it as well. Items that we should care about. The first and foremost is the number of connections that we have between our Spark cluster and our Scylla cluster. You will see in the demo that I will show in a minute that the amount of connection is basically created by the amount of executors you provide for your Spark cluster. So every executor will create a single connection between the executor node and the Scylla cluster. That can lead to less efficient communication between the executors and the Scylla node. So we will talk about a little bit about the architecture, how to deploy a more efficient Scylla-Spark cluster from our perspective. All right. Let's talk about batches. Here we go. Okay. So as I said before, writes happen in batches. What does that mean to us? Okay. So batches can be great if we can guarantee that the aggregated CQL statement that we perform are always setting the same Scylla partition key. It is possible that this is the case. For example, if we stream the information based on a single sensor data, and that data belongs to one partition key, it means that every write that we're going to do is going to be always on the same partition, maybe a different row, but it's going to be the same partition. So batches are going to be very efficient at that point. However, there are cases where the batches are not working on the same partition, which means that the Scylla coordinator node will need to handle a larger amount of data. Think about it. You have to bring multiple or write multiple partition keys, and each one of them should be going to a different node. So the coordinator node have to hold that information and wait for the acknowledgements to come back from the Scylla nodes, and that can create a burden on that specific coordinator, mostly around the memory, as well as the I/O system as well. Therefore, the connector makes an effort to control the batch processes. The first item that we will be discussing is the batch grouping buffer size. The default is 1,000, which means that every Spark task will aggregate up to 1,000 batches before actually accessing to the Scylla cluster. The benefit is a reduced chatter between the Spark node and the Scylla cluster. The disadvantages are latencies and actually reduced throughput, because your Spark cluster is actually waiting to aggregate enough batches. The next thing we're going to talk about is the output batch grouping key, which defines how the connector groups the batches. Remember, we spoke about the default on batches that the requirement is to have the same partition for all those batches. That's how is the default for the connector itself. The connector will try to group all the partitions that he sees for all the partitions for the same partition key into a single batch, and it will try to do that effort. However, if we know that there is a large discrepancy or dispersity on the partition keys, we might benefit from actually changing the grouping to either a replica set, so it means that the batch will try to understand which replica should get that batch coming in, and then it's actually going to group a number of SQL transactions for that specific replica and then send it to Scylla. Or the other way around is completely no. So do not look on any grouping key at all. So you just, every time you have a write, there is no aggregation on the batches, and you just submit it to the Scylla node and hope for the best. Other thing that we have to look at is batch size by bytes. It's basically being overridden if you have rows, the amount of rows that you have, and the default is 1,000 rows per batch. Other thing that you have to look at is the output concurrent writes. It means how many batches you're going to have in flight in every certain point in time. The default is 5. If you have a very performant cluster with a lot of data and a lot of execution power, you might want to increase that and get more batches in flight at every single time. The disadvantage on the other side, if that happens, you might overburden the Scylla cluster if you don't have enough I/O capacity or CPU capacity on the other side. So you have to very much take a look at the performance metrics of both Scylla and Spark to make sure that you have the right batch setting from both Scylla as well as the Spark side. Until now, we spoke only about the write processes. Let's look a little bit more into the read one. Sorry. Okay, there we go. So when Spark reads from Scylla, it does it in chunks of 64 megabytes. That's the default. Remember that every time we read a chunk of data, if you remember the previous slide, we actually do a table scan because we're trying to bring multiple partitions into an RDD. what happens with those table scans, that can cause latency and throughput decrease in your performance. What we do recommend is actually decreasing the size of the split size. So read a smaller chunk of data every time and reduce those big scans on the partitions and the table themselves. It will enable us a better concurrency and enable us to get a better throughput out of the Scylla node. Other thing that you have to think about, and sometimes we see it with customers, they think that they have, for example, 1 gigabyte of data on disk. That's fine, that's data on disk, but the data on disk is compressed. Once you bring it back to the memory of your Spark cluster, it's gonna be probably 1.6 gigabyte or 1.5 gigabyte. That, if you have not planned correctly your Spark cluster, can cause out-of-memory issues or a complete miscommunication between your Spark cluster and your Scylla cluster. People come and say, hey, but my Spark cluster just crashed, it cannot work with your Scylla. In many cases, it's just miscommunication or misunderstanding, misconfiguration between the amount of data you have in the Spark nodes versus the actual size of the data. So be cognizant about that setting to make sure that you don't override that workload. Other thing that you look at is the amount of rows you fetch in every CQL read. The default is 1,000 rows fetch. You can change it if you have larger partitions to read. However, I would be very, very cautious of doing that to understand exactly why you're doing those large partition reads from your cluster. So let's talk a little bit how we deploy Spark and Scylla. Okay. The first thing that we always hear is to collocate or not collocate. The first notion when customers come in and say, hey, I want to collocate my Spark cluster together with my Scylla cluster. The benefits are pretty obvious. You have less nodes to manage. Data is closer to the Spark nodes. It sounds like a very natural way to do that. However, there are multiple challenges in that architecture. First and foremost, Scylla is a resource-hungry application. Meaning, if you deploy Scylla without setting the exact number of cores, memory, and IOU actually assigned to it, it will take the whole node. Same thing will happen with the Spark executor. So if you did not set it up correctly, it means that they are going to be competing for the same resources. Neither Spark is going to be happy, nor Scylla is going to be happy at that moment. And it means that you have to very much plan for that capacity, both for the Scylla side as well as for the Spark side, and then it can cause you to basically over-provision for no good reason. Other items that happens in terms of memory sharing, if Spark doesn't have enough memory, as I said before, it will out of memory, and then one of them might crash the node with no good reason and basically hurt the other side. So from our perspective, when we look on not to collocating, so have a Spark cluster and a Scylla cluster, we see a little bit more benefits. First, today's architecture have a very powerful systems. 10 gigabit networks and low latency networks are something that is pretty common in architectures that we see today. So the challenges of network and latency from the network are less common. By not collocating, you actually have more controllability on your system. Think about it, if your Spark jobs are something that you just deploy once in a while, and you're in a cloud environment, you might spin up the node, run your job, get your results, and close those nodes. It means that your capacity planning is much more accurate. You spend less money on resources that you don't need. And in most cases, it's possible to automate those provisioning and get the benefit. You get the performance that you actually expect to get. So if you have a Spark job that needs to be completed in a very short time, you know exactly how much executors you have to define and how much nodes you have to put out there. And it helps you assess the right performance from your perspective. So from our perspective, we prefer that not to collocate. It's easier to manage. It's easier to get the performance out of both Scylla and Spark at the same time. Okay, let's continue. Let's talk about performance for a second. Okay. So if you look on the default that together you get from Spark today, the default, as we said, the number of parallelism Spark executions is 1. If you want to have on multiple Spark executors on a same machine, increase the parallelism of that specific Spark deployment to the number of cores that you have in that node. It's pretty easy to do that. You just define the number of cores you have in each one of your Spark slaves, and you're good to go. Reduce the split size from 64 megabytes to 1 megabyte. That will help us get you a better streaming of information from the Scylla cluster to your Spark nodes. Look at the connections, max connection per executor. Again, the default is 1. Make sure that you change it to the number of cores you have in each one of your executors. It will help us, again, get more connection to the cluster and more throughput from Scylla as well. As we spoke before, look at the output concurrent writes, which the default is 5 batches in flight in every moment of time. And look also on the concurrent reads, which the default is 512 rows, and in cases that you might want to increase it or decrease it based on your workload. So you really want to understand how the workload is executed. With that, I will go back to the demo. Hopefully the job completed. Yes, it did. Okay. So what we did here on the first execution that we sent out is basically, and I'll explain in a minute what we have here in our screen. So we had a table that we loaded. I'll go back to my Scylla cluster. I loaded the table that has flight delay information into a table. So if I'll just select star, and we'll do a limit 10. You can never type in public. You'll see that we have information that basically says what's the origin, destination, the date of the flight, whether it was canceled, and the delay information about that flight. This data set has something like a 1.2 gigabyte of information that is stored in a Scylla table. It comes from a CSV file that has multiple rows. So the Spark job basically take that information, that raw information, does some ETL on top of it, and push it into Scylla. And the first job that we did on that specific loader, and I'm going to talk about something that I did before we started the webinar, we basically said the following. Let's take 4 Spark nodes with 8 core each one of them, okay, and not apply any of the Spark connector performance settings that we have. What happens at that point, we will have 32 gigabytes of RAM and total of 32 executors or 32 cores. Remember, 4 nodes, 8 cores, each one of them. That loading of data took, at that point, 4.9 minutes. Later on, we changed it. Instead of having 4 8-core machines for Spark, we changed it to 8 machines of 4 cores, each one of them. What happens at that point, from Scylla perspective, let's see if the gods of demo will play along with me. Yeah. Okay. I'll go back to that execution. There you go. Okay. I'll go down a little bit just to show the benefits. Okay. In terms of ability to push information into our cluster, I'll do a small zoom in. Okay. In terms of our ability to push information into the cluster, with the 8 nodes, 4 core each, we got a much higher throughput than we got with the 4 8 cores. The reason for that is the amount of parallel transaction that we were able to ship into Scylla was actually bigger by roughly 20%. And this is how we got basically a more performant result of almost 1 minute less for doing that. When we apply a smaller Spark nodes, more Spark nodes to create a more concurrent execution, and we applied all our settings that we talked about, the amount of concurrent writes and the settings for the location of the partitions themselves in the Spark node. That's on the right side. On the read side, we did the same thing when we read information from the table. Basically, what we saw, and the same trick. We had first we had 8 4 cores Spark cluster. It was able to execute that job in 21 seconds. When we had 4 8 cores, it was roughly, again, 30% slower. This is the benefit of concurrency and parallel executions between Spark and Scylla. And with that, I'll go back to my presentation. That's our demo. I'll go back to present mode. Okay, so the conclusion of this session says, Scylla enables analytics on top of transactional data. You can do that. We definitely think it's a viable solution. However, performance tuning is required for certain workloads. If your workload has large partitions, you might want to increase the amount of rows you fetch on every CQL. If you have a very high write rate, you might want to define none for the partition batching parameters in the Spark connector. Resource management is also very important for the stability of your deployment. So you actually want to understand how you provision Spark if you collocate with Scylla. So make sure that you don't collide on the resources themselves, and how you actually get information out of Scylla through your Spark nodes in a manner that does not create either a full table scan on Scylla or create your starvation on your Spark nodes. And if you want to look how we have those demos about Scylla, so I will highly recommend you guys go to our the Docker-based deployment example that we have on our website. It was written by one of our team members, as well as there's a good resources about the Spark connector coming from Russell Spitzer from DataStax. It has a very good blogging around how to tune the Spark connector for best performance. And with that, I will open the session for questions and answers. Just want to say again, both the slides as well as the recording of this webinar will be sent to anybody who attended or registered for this webinar. And with that, I will go to the Q&A. Hopefully I can do that. Okay. So the first question that I have is, this is Spark standalone? Yes, this is Spark standalone. It's easy to deploy. It's a Git clone that you, sorry, it's a charges that you download. You open the charges and set up all the configurations yourself, and you're good to go. Do you have the Spark worker nodes running on the same node as Scylla? The answer to that is no. We separated the clusters here. It's a Scylla cluster and a Spark cluster. In that specific demo that you've seen, we have 3-node Scylla cluster and 8-node Spark cluster. When I changed the number of cores between 4 and 8, when I wanted to change the actual throughput I'm going to get from the Spark versus Scylla. Have you tried running this on a Spark on Yarn? No, I did not try to do that. It's a good idea to look at it. Other questions that I have here. What should be the default configuration for Scylla and Spark? Okay, I guess that you're meaning that what should be a default configuration. In this specific demo, we have 3 nodes of i3 2x large for the Scylla, as well as for Spark nodes. That is a 8 vCPU node with 60 GB of RAM and 1.9 terabyte of NVMEs. And that will provide you a decent performance. However, if you need a more performant system, I would argue that you can scale up the Scylla node, increase the number of cores as well as the memory to get more throughput. Okay. Okay, I marked more here. Okay. If separate the cluster, oh, so it's a follow-up questions. Okay. So the question was, if those are separate cluster, how does data locality come into play? Data locality come to play that the Spark sends the request to the connector. The connector, since he knows the same hashing function that Scylla is using to store information at different nodes, it will fetch the information from the Scylla cluster. There is no per se data locality like you would get with Hadoop. For example, when you run Spark, that it knows exactly that the HDFS, the Spark job will be sent to the node that is sitting on top of that specific block size. The data will be communicated over the network. Okay. What else? Looking at the other questions. Okay. Is Scylla and Spark tuned configuration available for deployment on Kubernetes managed container orchestration? We are just sending out our Helm chart for Scylla. We are just have send a pull request to the Google repo, hopefully to have that one pretty soon. We do not have a Scylla and Spark tuned configuration for Kubernetes. Good idea. Definitely we'll take a note of that and work towards having that one available. What else? Does Scylla send data compressed or uncompressed over the network? So Scylla send data compressed over the network. It will be compressed by default. You can disable that one if you want. That's okay. One more here. What tuning option would you recommend for a very high write workload? For the very high write workload, I would definitely look at the way you send information in terms of the actual partitions. If those are white partitions and you know that you're always working on the same partition, then I would, for example, the partition aggregation, I would say keep the aggregation based on the partition. However, if you know that you have a very dispersed partition key, I would maybe disable to none. And the reason for that is that you will be able to, every write that has to go into Scylla, go immediately from Spark to executor to the Scylla node without, aggregating in the Scylla, in the Spark machine. Other thing that you have to look at is the actual amount of Spark executors you have versus the Scylla nodes that you have. I would argue that you would prefer that point to have more Spark nodes with less cores, each one of them, just to enable for yourself a better concurrency from your Spark to the Scylla nodes themselves. Okay. I think that's the questions that I got. So again, I want to thank you everybody for attending this webinar. As I said before, we will be sending both the slides and this recording link. We will probably publish a blog about the questions and answers, so you'll have that one as well in written. I want to invite you for our next month webinar. It's going to be with our great Glover Costa. It's going to be about how Scylla uses control theory to handle compaction. And with that, I will be closing this webinar. Thank you very much again for attending this webinar.